Hello, I'm Roseval, a master's student from the Computer Science Department at the University of São Paulo. I'm here to present our research on the Explainable LightGBM approach for predicting myocardial infarction mortality. This project is the result of a collaboration between Malaquias and myself during our final project in the Machine Learning Introduction course under Professor Rosalia's guidance. Here we have a presentation overview. First, we introduce the problem that we aim to tackle. Then, present our literature review that supports the exploration of the identified problem. Next, represent the objectives that guides this study. Then afterward, we outline the methods and materials employed, describing the experiments conducted and how we evaluated the results. Finally, we discuss the experiments performed and the results achieved. Then we conclude with a summary of our contribution and potential future works. So first, we'll delve in the background of our research, presenting the research problem and providing insights into the motivation behind this study. Cardiovascular disease, or CVD, is the leading cause of death since the 90s. About 80 million people die annually around the globe. Also, in Brazil, over 397,000 deaths were attributed to CVD in 2019. In particular, heart attack or acute myocardial infarction, also known as AMI, is a significant contributor to CVD-related deaths. Also, AMI results from the decreased or blocked blood flow in the heart's coronary artery. So in general, medicine can significantly benefit from the implementation of a predictive model for this specific problem, given that the adoption of an interpretive predictive model offers the opportunity to support physicians during diagnosis, providing them with confidence in the decisions made. So, given our literature review, we identified that the focus of the majority of studies is on early identification of AMI cases, using machine learning techniques such as in the second study that performs the early prediction of AMI and patient mortality among individuals experiencing chest pain, and in the third study that performs the early prediction through novel molecular biomarkers present in the immune cells associated with AMI. Also, we identified a rise in studies that tries to predict the mortality of AMI cases, such as the studies 3 and 4, aim at predicting MI-related mortality, achieving accuracies of 80% and 86% respectively. Studies 5 predicted post-MI complications using a multi-layered neural model coupled with explainable tools. Deep learning algorithms face preprocessing challenges, potentially introducing bias when dealing with heterogeneous data in tabular formats. And the sixth study compared deep learning to the tree boosted based techniques such as CGBoost, LightGBM, and CatBoost, with those models showing superior performance. Also, medical domain struggles with interpretability of black box models. Given this, the tree-sharp technique emerged as a solution to erase transparency. For example, in the 7th study, it is used tree-sharp with CGBoost for cardiovascular disease and type 2 diabetes mellitus patients, improve transparency and trust in the trained model. So next, for the studies that supports and motivates this study, we have the following objectives. First, we aim to develop machine learning models for predicting mortality in AMI patients, using primarily gradient boosted decision trees methods like CGBoost, LightGBM, and CatBoost. With this, we hypothesize that using simple algorithms for preprocessing may limit the ensemble boosted tree model's performance. Thus, to validate this, we conducted an ablation study to analyze model performance with and without specific preprocessing components, evaluating if these models eliminate the need for imputation, feature selection, and target feature balance. Lastly, Tree-shape method is employed for interpretability of the training model. So, for the methods and materials employed in this study we have first the dataset. This dataset is called Myocardial Infarction Complications dataset, and it was obtained from the Krasnoyarsk Interdistrict Clinical Hospital in Russia, collected in the 90s by the University of Lancaster and made publicly available in 2020. This dataset includes patient-specific information and data points at different time intervals, allowing tracking of disease progression over 24, 48, and 72 hours. The dataset's temporal and detailed nature facilitates the understanding of disease progression and outcomes, considering the variability in individual cases. This dataset comprises of 1,700 instances, each with 124 features, including 111 input characteristics, distributed between numerical, binary, and categorical ordinal data. And finally, it presents 12 potential target labels. Approximately 7.6% of instances contain missing values. So, the focus of this dataset is on complications leading to mortality, accounting for around 15.94% of instances, with categories as shown in this table. Thus, the majority of instances correspond to individuals who survived, providing an unbalanced dataset for analysis. For the materials used in this study, our experiments were implemented in Python, using the libraries Panda for data manipulation, skitlearn for pre-processing and some of the training models, and for the tree boosting algorithms, we use the libraries XGBoost, CatchBoost, and LightGBM. All implementations are available on our GitHub repository. So, for the pre-processing task, we perform the following steps. First, data cleaning, that we remove features with more than 10% missing values, eliminate columns with single value dominance exceeding 95%, resulting in a dataset of 61 columns. Then, binarizing the target class, which we group lethal complications into deceased and unknown, which is alive, resulting in an unbalanced dataset. Then, we perform a dataset splitting that divides the dataset into training, which comprises of 80% of the dataset, and testing, which comprises of 20% of the dataset. We did this to perform a final test, testing the model in a scenario which it's never seen the data before. Then the next step is dataset balancing, which we apply random undersampling to address class imbalance by adjusting the minority class size with a ratio of 0.5%, based on superior performance for predictive models in this context. Then, we perform wrangling missing data. For categorical data, we fill missing values with the mode. For numerical data, we replace missing values with the median. Then, we converted all attributes to numerical format, including binary and categorical ordinal data, used one-hot encoding for categorical nominal columns, and label encoding for categorical ordinal data. Also, we applied normalization, scaling values within a range of 0 to 1. For a selection of the most important features regarding the class, the assistance of domain professionals, in our case doctors, would be necessary for the extensive 61 attributes. Thus, we adopted a feature selection algorithm. The SelectKBS method employs statistical tests to access and rank features according to their correlation with the target variable. Using the chi-square, this method is especially designed for testing the independence between two categorical variables. Features demonstrating a substantial correlation with the target variable receives an elevated score for the case selection. Given the considerable prevalence of categorical variables within our dataset, the utilization of SelectKBS proved to be particularly apt for addressing the requirements of our specific problem. Thus, we mitigated the manual analysis challenges with this. We choose to use methods with feature selection and imputation based on measures of central tendency and statistical tests, respectively. Hence, we don't rely on machine learning algorithms for a feature selection and imputation that can add unnecessary complexities to our problem. So, here we have our pipeline for model selection. We made this so that we can select our best model to test in our split of 20% of data set. So first we conduct a hyperparameter tuning with grid search with 5-fold cross-validation on the 80% trained data. We accessed multiple models including multi-layer perception, support vector machines, logistical regression, decision tree, random forest, and our ensemble boosted trees, XGBoost, LightGBM, and CatBoost. It is important to note that we fine-tune hyperparameters with and without preprocessed pipeline during grid search. In the hyperparameter tuning, we prioritize F1 score metric during grid search due to the imbalanced nature of our dataset. Also, we emphasized recall and F1 score over accuracy to minimize false negatives in the medical context. Next, we evaluated each model with optimal hyperparameters through 10-fold cross-validation on the training set. We access metrics includes accuracy, recall, precision, and F1 score. Then, we selected the best model based on these metrics. Finally, we trained the selected best model using the training set, which comprises of 80% of our dataset, and test the training model using the test dataset, which comprises 20% of the entire dataset. With this, we conducted a quantitative analysis on the metrics of the final model to determine the viability of applying the predictive model in a real-world context, given the 20% of the dataset never seen by the model. For the selected hyperparameter space, we focus on decision tree-based algorithms, given that we handled a substantial quantity of categorical attributes. We use consistent hyperparameter settings for individual tree models, introducing variability exclusively in gradient-boosted tree models. Initial experiments revealed susceptibility to overfitting on training data. Thus, the primary emphasis of this fine-tuning was to mitigate model complexity. However, it is important to note that we also tested algorithms such as MLP, SVM, and LNR. So here, we have the results for the 10-fold cross-validation for each model with preprocessing with its optimal hyperparameters. Given the practical implications in suggesting immediate hospitalization for MI patients, we prioritize minimizing false negatives. Thus, it's emphasized achieving high recall for the model's effectiveness. As you can see, RF exhibited the highest recall among all evaluated models and a commendable F1 score, indicating a harmonious balance between precision and recall. However, by performing a statistic test, we arrived at an inconclusive result when comparing the RF model and CatBoost. Thus, we could not affirm that they are different in performance. In this study, we investigated the application of various machine learning methods, with a specific focus on gradient-boosted tree techniques. We also postulated that the utilization of simple algorithms in feature selection, imputation, and target feature balance staging may constrain the performance of these methods, as they inherently deal with feature selection, mission values, and imbalanced datasets. Thus, an ablation study was also conducted to assess the performance of boosted tree models using two distinct pipelines. Here we can see the two pipelines. In pipeline 1, we executed the procedures for data preprocessing and feature selection as described. In contrast, pipeline 2 utilized the raw dataset without any alterations, employing the data exactly as it was received. The study found pipeline 2 models outperforming the first pipeline. LightGBM, CatBoost, and XGBoost perform similarly to the models without preprocessing. Notably, the best preprocessed model, in this case RF, showed no significant difference from the best non-preprocessed model, in this case LightGBM. This study highlights the significance of a non-preprocessed model, given that this approach simplifies implementation. So the LightGBM model without preprocessing and the RF model were chosen as the best models that we have, with no significant statistical difference in the ablation study. However, in the final test, LightGBM showed superior metrics. Evaluation of the test dataset indicates consistent performance in practical scenarios. The final predictive model, with a high recall of 90.3% and an F1 score of 91.2%, is deemed suitable for recommending hospitalization of AMI patients, demonstrating reliability. Using the SHAP method on the LightGBM model with pipeline 2, we explored key features influencing predictions. Visualizing data aids in knowledge discovery. SHAP grounded in game theory measures each feature's contribution to machine learning predictions. Shapley values highlight prediction differences when a feature is included or not. In this study, the 3-SHAP algorithm, tailored for tree-based models, was chosen for analysis. In Figure 1, it is depicted Shapley values for each feature, illustrating their impact on predicted outcomes. The B-swarm plot arranges features by relevance, highlighting systolic blood pressure, time to hospital admission, and pain relapse on the third day as most influential. Certain features like pain relapse, age, white blood cell count, and the left ventricular infarction positively correlate with mortality risk. On contrary, elapsed time and opioid use in the emergency department are negatively related to risk. This plot suggests that a shorter time to hospital reduces mortality risk, emphasizing the importance of a swift medical attention. So, in conclusion, we explored various machine learning methods, focusing on gradient-boosted tree techniques demonstrating their remarkable effectiveness compared to previous studies. Among the models, LightGBM emerged as the top performer on the test set, achieving an impressive F1 score of 91.2% and an accuracy of 91.8%. Using 3-SHAP to interpret the LightGBM model, it was identified the systolic blood pressure, time elapsed from attack to hospital admission, and the relapse of pain on the third day as the most significant factors influencing predictions. Thus, we developed a predictive model for recommending hospitalization in AMI patients, providing statistically and interpretative medical diagnosis with a SHAP-based solution. Given our cross-validation tests performed, we do not observe statistically significant differences between models of pipeline 1 and 2. However, the LightGBM model without preprocessing presents the highest performance on the final evaluation on the 20% test dataset. Thus, as future work, we intend to gather more updated data and try to validate again our hypothesis with other machine learning techniques, emphasizing the potential broader applicability of the explored idea of advantages of gradient-boosted trees models without any data preprocessing. We would like to thank the financial agencies that helped in the publication of this work, in special FAPESP, CAPES, and CNPq.